In this video, we're looking at the factors and zeros of a polynomial function and the relationships between them. We have some vocab up at the top. The zero of a function is a solution of the equation f of x equals 0. The zero of a function is also called a root. And then as a reminder on a graph, that would also make an x-intercept. We need to realize that all those words are talking about the same thing. So start out with trying one from our prior learning. Let's find the zeros of y equals x squared minus 2x minus 8. You can pause the video while we do that. So I just solved this two different ways. I solved by factoring first, and that's over here. And when I solved by factoring, I set each factor equal to 0, and I got x equals 4 and x equals negative 2. I also could have solved that by quadratic formula. And that would be, both of these would be algebraic methods. Or I could solve by graphing, which is what I did in the picture of the graph, and looking for the x-intercepts, which the x-intercepts were 4 and negative 2. So those were the solutions, or the roots, or the zeros. So at this point, we should be able to find the zeros of any polynomial. The difficulty arises when we have to factor a polynomial with a degree bigger than 2. Remember the degree, that was the biggest exponent. What if we're given a polynomial that was already in factored form? Could we find the zeros then? Of course, you say to yourself. And in number 1, it asks us to find the zeros of this function. Remember, when finding the zeros of a function, you really want to know what values make the equation equal 0. So we would just take each factor and set it equal to 0, which would give us x equals positive 1. If we set the second factor equal to 0, that would give us x equals negative 3. And if we set the third factor equal to 0, this one involves a little more algebra, but we could move the 1 over by subtraction and divide by 2, which would give us x equals negative a half. So we would have 3 zeros for this function. We could write them separately like that, or we could write them in the curly brackets. If we write them in curly brackets, then typically what we would do is we would start out and we'd write the smallest one first, then we would write the next smallest one, and last we would write the 1. So that's another way we could express the zeros. So if we wanted to use this information, it says for number 2 to graph that same function and identify the x intervals where y is increasing and decreasing. So if we had to graph this by hand, we would know that the 3 zeros that we got when we factored are going to be the 3 x-intercepts. So x equals 1, x equals negative 3, and x equals negative 1/2 all have to be on our function. So they have to be points on the x-axis. We should also be able to determine the end behavior. When all of the x terms are multiplied together, so if we multiplied that whole function out, we would start out and we would have 2x cubed and then we'd have plus some other stuff. But really it's that first term, the 2x cubed, that tells us what the end behavior should be, because that's the most powerful. If we plug in really big numbers for x, let's start out with x approaches negative infinity. If we plug in really big negative numbers for x, a negative times a negative times a negative is a negative, so the y is going to become a really big negative number. So as x approaches negative infinity, y approaches negative infinity. If we plug in really big positive numbers for x and we cube them, we'll get a positive number. So as x approaches infinity, y approaches infinity. So this combined with the zeros will give us a basic shape of our graph. So we should be able to tell that over here on the left side, as x approaches negative infinity, I'm down. And over here on the right side, as x approaches positive infinity, I'm up. If I have to cross at 3 places in between, I'm going to have to do something like this to make that happen. So if we want a more accurate graph, we're going to use our calculator to put this function in. So to put this into my calculator, I'm going to go into the graph menu and I'm going to type it in just like it's written as x minus 1 in parentheses, and then x plus 3 in parentheses, and then 2x plus 1 in parentheses. Once I've got that in, I want to go to Shift View Window, which is F3. Oops, I didn't hit the right button. Hold on. Shift View Window, which is F3, and I want to go to a Standard View Windows, which is F3. On your TI, you just hit Zoom 6 for Zoom Standard, and then I can graph this. So that looks pretty good. It looks basically what I thought my graph was going to look like over here, just doesn't have as many specifics. So now what I want to do is I want to take this information from my graph and I want to transfer it over to a grid. In order to know exactly where the peak and valley is, I can go to GSolve, which is F5, and this high point on my graph is going to be the maximum, so I hit F2 for maximum. It tells me that that peak point up there is at negative 2.9. So I can come onto my graph paper over here, and my maximum is at negative 2.9. So I can go to the point negative 2.9 and plot that. I also want to find my minimum, or in this case, my low point on my graph. This is my maximum. Maximum is the big one, minimum is the low one. So let me go back to my graph, and I can just repeat this process where I go GSolve min, and it will tell me the y value and the x value of my minimum. Now this is not quite so pretty. I could tell my x is 0.3 repeating, so I'm going to call that 1/3, and the y is negative 3.7-ish. Okay, I'll write it down to 4 decimal places when I write it, but it's hard to plot that. So I write down my minimum, and then I plotted this point on the graph as well. All that's left to do would be to connect the dots. I could also, if I wanted to, go over to my calculator and then go into the table menu. And I always need to reset my table because my calculator memory resets every time from negative 10 to 10. And then I can make my table. I could also look and see if I scroll down this list, are there any nice points that I want to plot? Negative 3.0 is already there. Negative 2.9 is already there. Negative 1.4, that's a pretty nice point. So I'm going to come over and graph negative 1.4 on my graph. Let's see what else I have that I could plot. If I keep on scrolling down here, I've got 0, negative 3. That's my y-intercept. I'm going to put that one on there. And then 1, 0 I already had on there. So that's about all that's going to fit here. I'm going to connect these dots. And there's my graph. So I need to state the intervals where the function is increasing and the intervals where the function is decreasing. Remember that when we were doing increasing and decreasing in the past, we always wanted to go from left to right. So increasing would mean going up and decreasing would mean going down. If I look at my graph going from left to right, on this part of the curve, I'm going up, so I'm increasing. If I have to describe those x intervals, if I were to label the end of this point right here, that was when y was at negative infinity. X was at negative infinity. I had this arrow over here on the right, which as x went to positive infinity, y went to positive infinity. I had the point of my maximum, which was at negative 2.9. And I had the point of my minimum, which was at 1/3, negative 3.7-ish. So if I'm using the x values here to describe where I'm increasing and decreasing, I'm starting at negative infinity and I'm going until I reach negative 2. So I'm going to say from negative infinity is less than x is less than negative 2, I'm increasing. Then my graph changes and it starts decreasing. This whole time it's going down. When is it going down? Well, again, the x value where it started was at negative 2. And it stopped at the x value of the minimum, which was at 1/3. So I'm going to say that my function is decreasing from -2 is less than x, which is less than 1/3. Then I have one last branch of my function where I start going back up again. The x value where I start going up is at 1/3, and I continue going up forever. Again, the x value there is positive infinity. So I'm going to write from 1/3 is less than x is less than infinity. I'm increasing. So I've used my calculator to find the maximum minimum and then described where I'm increasing and decreasing based on those turning points. That's another key word we should know, the turning points. The turning points are the maximums and the minimums, anywhere the graph changes direction from increasing to decreasing or vice versa. Here's another example in number 3. I want you to find the zeros by hand, plot the zeros by hand, use your calculator to graph it, find any maximum and minimum, and then find the intervals for increasing and decreasing. You can pause the video while you do that. So I plotted my zeros, and then I graphed it on my calculator to get some more points. I found my maximum and minimum. They looked like they were at nice integer points, but when I actually calculate them on my calculator, I can see that this maximum and this minimum really are not quite on the nice grid marks. To decide where I'm increasing, that's where I'm going up from left to right. So on this branch, I'm going up from left to right, and on this branch, I'm going up from left to right. So I'm going to have two intervals, and I describe them in terms of their x values only. So my x values would be the x value of the minimum, or the maximum. So from -infinity to the maximum I was increasing. And then from down here at the bottom, which is the x value of the minimum, to forever, which was positive infinity, I was also increasing. To decide where I'm decreasing, that's on this branch right here. So I need the x value of my max point, and then I stopped decreasing at the x value of my min point, and I put them in. We need you to be able to go backwards as well. So what if you were given all of the zeros of the function? Could you write the function in factored form? Sure. If my 0 was x equals 2, then my factor is x minus 2. If my 0 is x equals -3, then my factor would be x plus 3. If my 0 was x equals 1, then my factor would be x minus 1. This is a polynomial expression right now. It's not an actual function until I put something out in front, like an f of x or a p of x or a y equals, something like that. It didn't say we had to be in standard form, so I'm just going to leave it in factored form. On number 5, it says, without adding another 0, can you find another polynomial function with the same zeros as in problem number 4? Why or why not? If this is possible, please write it down. So what I want to know is if I can keep the zeros. In order to keep the zeros, I have to keep all the same factors. If I want to make the graph different or the function different, what could I do to this where I could keep these same 3 zeros? Well, what if I flip this over? Would I still have the same 3 zeros? If I flip it over, it would still have the same 3 zeros, but it wouldn't add any more. How could I do that? Well, I could put a negative out in front, and this would be a new polynomial function. I could also stretch it if I wanted to. I could make this thing go up higher and come down lower. So I could have done something, I'm just going to call it g of x for a new one. I could have put like a 2 out in front to change it. I could multiply by any constant, so any nice number, and that would still give me the same zeros. I can't add or subtract on the end because that's going to move me up and down and change my zeros, but any nice number I can multiply by. So pause the video while you do number 6 and number 7. So my original polynomial here would have factors of x plus 2, x minus 5, and x minus 0. Or if you wanted to, you could rewrite that last one as just an x there rather than x minus 0. If you wanted to do this without adding another 0, could you make another polynomial function? Well, if you multiply by a constant, the other thing I didn't mention last time is we could have added any exponents we wanted to. If I make these squareds or cubes or to the 5th powers and I raise the power on the factor, it's not going to make another 0. It's just going to change the function. All right, on number 8, it says sometimes an additional step is added, writing the polynomial in standard form. When you do this, just stay organized and multiply 2 of the binomials together at a time. It can be tedious, but it shouldn't be too difficult. This one says write a polynomial in standard form with zeros at -4, -2, and -1. So that means our factors are y equals x plus 4, x plus 2, and x plus 1. So if I want to multiply these two things together, I'm going to start out and first I'm going to multiply these two together. So I have x plus 4 times x plus 2. I'm going to multiply using boxes or my area model. And when I multiply my parts and I put them together, I would wind up with x squared plus 6x plus 8. Now I still had from the original problem my x plus 1. So now I'm going to need to multiply these two things together. So I have x squared plus 6x plus 8. I'm going to multiply that by x plus 1. So now I have 3 terms times 2 terms. So I'm going to have more in my boxes. X squared times x is x cubed. X squared times 1 is 1x squared. 6x times x is 6x squared. 6x times 1 is 6x. 8 times x is 8x. And 8 times 1 is 8. Then I just need to group together. I've got an x cubed, so I'm going to write that one down. I have 6x squared and 1x squared makes 7x squared. I have 6x plus 8x makes 14x. And on the end here I have a plus 8. So this is my function. Again, if I want an equation, I need my y equals back. This is my function in standard form with the biggest x first, working our way down. Now, some polynomial functions have multiple zeros. This is when a linear factor is repeated. For example, in this function, y equals right here, there's a multiple 0. That x plus 3 factor could have been written twice as x plus 3 times x plus 3. This means that when you go to write your zeros, x equals -3 is a multiple 0. So we want to say that that's a 0 2 times. We call this the multiplicity of the 0. So when we write out the zeros, we can say that the zeros of our function are 1, 2, -3, and that -3 has a multiplicity of 2. We only talk about multiplicities of 2 or more because if a multiplicity is 1, it's not really a multiplicity, it's just a 0. So let's state the zeros of y equals x squared. So I've got x squared equal to 0. So x would equal 0. That's going to have a multiplicity of 2 because it's a 0 twice. My next factor is x minus 1 to the 4th. If I set that equal to 0, I get x equals 1. Since the exponent was a 4, I'm going to say this has a multiplicity of 4. Going to my next 0, I have x plus 5 equal to 0, which gives me x equals -5. I don't need to write down that that has a multiplicity of 1 because it was only a factor one time. My last factor was 3x minus 2. If I set that equal to 0, I add 2, I divide by 3 to get x equals 2/3, and again that one would have a multiplicity of 1, so I don't need to write it. These are the zeros with their multiplicities. When we're talking about the multiplicity of a zero, some different things are going to happen in the graph of the polynomial. So let's look at our calculator to compare some of these graphs. We're going to be looking at what happens at the root x equals -2. You can see all of these things that we're going to graph have factors of x minus 1 and x plus 2. The factor of x plus 2 gives me the root of x equals -2. And then as we graph, we're going to change the exponent with that factor and take a look at what happens. So I want to pull up my calculator. So here's my graph for A. I've graphed the function x minus 1 times x plus 2, and it asks, what is the graph doing at x equals -2? Well, the 0 at x equals -2 is right here on my calculator. This isn't showing up. Oh, there it is. Okay, so the 0, I'm sorry, that's the 0 at x equals 1. This is the 0 at x equals -2. So this is the 0 we're going to keep talking about at -2. What is it doing right there? The graph looks like a line. The graph goes straight through. Okay, so if I looked at the 0 right here, it was just going like that. It went right on through. If this was my x-axis and this is my function, it goes straight through. So for part B, I took my function and I changed it to put a squared up there with my factor. If I look at the graph of this thing, now at x equals -2, something strange is happening. It's not going straight through like it did on the last one. If I had to describe what was happening there, the graph turns. So the graph has a turning point at that 0. Okay, and when I looked at it, if this was my x-axis, it was just making an upside down U where it touched. If I just looked at that one little spot right there, it was an upside down U if I just do that little tiny window. Okay, then I have to make my factor a cube. When I make my factor a cube, now my graph looks really strange. Again, if I just look at this tiny little spot right here, what's my graph doing? It's making the bendy shape. That's the shape that's associated with a cubic, and that was the multiplicity of this 0. So if we had to describe, we could say the graph has a bend point, maybe, but it goes through. It still goes through. Okay, and if I were describing it in my pictures over here, it made that little bend shape. Okay, how about if we graph the same factor to the 4th power now? If we make a graph that's to the 4th power, and I look at this 0 right here at -2, it looks like an upside down U shape. This is also a little bit flatter of a U. When I looked at the graph with the squared, the 0 is a little more rounded. This one's a little more squared off. When you draw it, not quite as squared off as I made it, but it gets flatter compared to the x squared one did. But it still touches and turns right there. So if I had to describe, I would say the graph has a turning point again. And if I wanted to make my little picture, there's my x-axis. It's going upside down. All right, how about x to the... So if we're going to graph with our x plus 2 factor to the 5th power, well, again, it's making a bendy shape right here at -2. Just like the last time when the cubic made sort of a gradual bendy shape, this one is a little more pronounced of flatness right there, but it still makes the bendy shape and goes through. So let's add that to a table. So the graph has a bend and goes through. Hopefully we can start to figure out what's happening here. What do we think is going to happen? Oh, wait, here, let me draw my picture in. Again, it looked pretty flat right there. Maybe we can make an assumption of what's going to happen when we do x to the 6th. If I do x to the 6th, this one again made the upside down U shape. I'm just looking at this one, and I know that this is a much sharp turning point, and it's a U shape because the multiplicity was 6. So here's our multiplicity of 6, and again, the graph has a turning point. Okay, now we've got a box over here. It says when the multiplicity is odd, the graph at that root. So let's look at our odd multiplicities here. We had 1 where it went straight through. We had 3 where the graph has a bendy point and goes through. And we had 5 where the graph has a bend and go through. So if we had to describe what happens at an odd multiplicity, we could say the graph crosses the axis, so it goes through. The next part of the question said, when the multiplicity is even, what happens? Well, at our even multiplicities, at x equals 2, we made a turning point. At x equals 4, we made a turning point. And at x equals 6, we made a turning point. So when the graph has an even multiplicity, the curve has a turning point on the axis. So it doesn't cross, it turns and then goes through. I also just want to point out the shapes for a second. When our multiplicity was 1, so we had a linear factor, we were nice and straight and went on straight through. When our multiplicity was 2, we made our bend shape, and that would look like a quadratic or a second degree function. When our multiplicity is 3, that's called a cubic if it were a function, and when I make my bend shape, I turn and go through. Notice I'm drawing 2 pictures for each of these because it's going to depend on which direction you're coming from, whether your U is up or down or your bend is left or right. Okay. Again, multiplicity of 4 was a quartic function, and if you look at these functions, the types of zeros you get will look like little quartics. If you're a multiplicity of 5, which is a quintic, you're going to look like a quintic function. You're going to have a bendy point, and it's going to be a little flat in the middle where you make your bend. You could go from the left or from the right, doesn't matter. To get a multiplicity of 6, again, it's going to make a U shape. This U shape is a little more extreme than the lower power U shapes, but all of the even powers make U shapes when they touch the axis, and all of the odd powers make going through or a bendy shape when they touch the axis. Okay, at the very end here we had a summary. It says equivalent statements about polynomials. You've got 5 questions where we need to fill in the blank. I'm giving you the words factor, root, solution, x-intercept, and 0. And I want you to go through and figure out which answer goes in which blank. You can pause the video while you choose and write them down. All right, so the first one, -4 is a solution of an equation. You solve an equation to figure out what x equals, so that's the solution. When we're talking about a graph, what happens on the graph is you'll have an x-intercept on a graph. Likewise, that's also called a 0, so -4 is a 0 of a function. We could also say -4 is a root of that function. And then x plus 4 is a factor of just the expression x squared plus 3x minus 4. So these guys, root and 0, we can really use those two interchangeably. So you could have had either one in either blank. That's the same thing right there. The solution of equation, the important part here is now we've set our function equal to 0. And the important thing about an x-intercept is it specifically relates to a graph. Factor is the only one where we worked it back into the little group, and it wasn't just an x equals, it was a little expression x plus 4.